Okay, before I jump into example 15, I wanted to kind of point out the general form of one of our Leslie matrices. So on the top row here, we have our birth rates. That's the exact same as what we did before, when I was kind of looking at what happens if I have n number of rows. So I just keep putting all my birth rates for the number of rows I have in my original population size. Now I go through and you can see from my second row, if you look at my top left, I have my first survival rate. And that also comes all the way down here like so. Just note, I should always have a 0 on the end of any of my Leslie matrices, as I never really consider the survival rate of my final population group. I kind of assume, like I said, the population ends after my final interval. So if I had more rows, this is kind of how I can always build my Leslie matrix. Birth rates on the top, come down a row, survival rates in a nice diagonal line, zeros everywhere else. Okay, sorry, I said earlier we would do example 15, but I've actually changed my mind. Let's just do example 16 instead. And some of those similar ideas in example 15, we'll just kind of talk about as we're going through and solving this particular problem. So if we look at my question, I have my Leslie matrix, I have my initial population. Now, there is a few pieces of information missing from the example I did with sheep earlier on. So one of the things that's missing is I don't have my age intervals here. So I don't have age intervals. I don't know if this is between 0 to 2 years or 0 to 10 years, or maybe even 2 to 15. I'm not really told my intervals I'm going to be looking at. Now, why that is important is because normally if I do PO and I do P1, it's one interval on from my original. So if my interval is 0 to 2, I've gone forward 2 years. If it's 0 to 10, I've gone forward 10 years. That information is kind of lost in the way this question is presented. However, all I'm trying to find in part A is just the long-term growth rate, find the long-term growth rate, which essentially just wants us to investigate what happens if I just look at, if I have L cubed or L to the power of 5 or L to the power of 10, is my population increasing or is it decreasing? Because that's what the question's asking. I don't necessarily need to know my intervals because I'm not concerned with the time period. I'm just concerned with, are we growing? Are we decaying? What is that growth rate over a period of time, or over the long term in this case? Okay, so for a long-term growth rate, I want to look at P of some large number for K. So I could do, really the bigger the better. If I have my calculator, I may as well just do something really big. Let's just do P of 200. So we'll do P of 200. That's going to be equal to L to the power of 200 multiplied by P naught. And we're going to figure out what this matrix is. Then we're just going to do one iteration on. So let's do P of 201. That way we can kind of compare the two. We can get our growth rate, or kind of like our growth rate proportion based on this idea here. This is going to be L201 PO. So for any of these long-term growth rate questions, do a high value of K and then do a high value of like K plus 1 is kind of how the textbook describes it, where I just do one iteration on from my original. And I can pick any large number. So I could do 200, 500, 1,000. I think 200 is going to be pretty big though. I mean, we saw we did 50 last time and it gave me a pretty large number. So I think 200 is pretty safe. Okay, so if I come over to my graphics calculator, I'm going to now do my two matrices. So I'll do my Leslie matrix, which is going to be 0, 2.3, 0.4, and I'll fill out the rest. That's going to be 0.6, 0, 0, 0, 0.30. I'm now going to store that as L for my Leslie matrix. If I try to put a capital L in and I click enter, it defaults automatically to a lowercase. So it's always going to be a lowercase L if I look at kind of my variable buttons. You can see I've got a lowercase L here. So now I'm going to put my population size in, 800, 800, and 800. I'm going to store that as being P. So for this example, we've actually all started off with the exact same size. So we've started off with the exact same size, and now we're going to look at what happens over time. So if I do L to the power of 200 multiplied by E, again, I'm going to get some ridiculously large numbers, but that's fine. Now I just want to do the same thing. I'm going to do one iteration on. Let's change this to 201. And again, I have some super, super large numbers. All I'm going to do now is going to take this term here. Actually, I can even do it. I can do it even easier. I'm now going to essentially divide both of my matrices here, and that's going to give me my proportion. So I'm going to divide my bigger one by my smaller one. Okay, so I can't do it this way, which is fine. So instead, I'm just going to divide one of my entries here by the other entry. So if I do my first entry here, so if I take this number, I copy that, paste that number in, I'm now going to divide this by my number I have all the way up here. And if I click enter, I get about 1.2. So you can see this simplifies down to a pretty nice ratio. And again, the bigger my group is, the kind of better idea I'm going to have. Obviously, my numbers are gigantic, so there could be easier ways to do this. If you can't copy and paste, you can simply just type. That's going to be 5. If I do the second one, 5.37479, whoops, 9, multiplied by 10 to the power of 18. Okay, I'm just going to copy and paste this down here. Just know this little e basically stands for times 10 to the power of, and then, I put 18 for this one. So I click enter, get about 1.199. So again, we're getting close to about 1.2 if I'm rounding up to one decimal place. And if I do my final one, I should be getting 1.2 right at this point. I think I'm pretty certain on that, but let's do the final one anyway. And I got 1.2. So I want to do all three, and I should find my population growth for each category. If I do any of these long-term Leslie matrices, should actually be quite consistent. Now, if I did 500, I might have found the 1.2 in my middle one might have been closer as well, or been exact with a couple of zeros on the end. So you can see we're trending around 1.2. So I'm going to say my growth rate for my population is 1.2. Or it increases by 20% is another way to kind of interpret these numbers here. So if I come back across here, I find my value for each of these, I divide the corresponding entries, and I get my growth rate is approximately 1.2. Now, I want to find the long-term ratio of the sizes of the three age groups. This is how those size groups are ratioed to each other. And again, I'm looking at the kind of the long-term ratios between the two. So the way I just did that part there in example 16 is the same way I do part 15 here, where I look at my population of K, some large K value. I look at K plus 1, and I divide the corresponding entries between those two matrices to see how much has my population grown from P of K to P of K plus 1. So to do part B, where I'm finding the long-term ratio of the sizes of my three age groups, all I want to do is want to put in some big values. Let's just do P of 201, L of 201, P naught. That's going to give me this matrix here. Now, to find my ratio between these groups, or to find a ratio between three numbers, I want to have one number that's consistent. That's normally going to be my smallest number. So this is my smallest number here in my matrix. Now, the first step is going to be to divide. I'm going to do 5.375 times 10 to the 18 divided by 1.344 times 10 to the 18. You might be able to see this is going to simplify away. If I had nicer numbers, this might be possible. I'm just going to use my calculator to give me an idea. So if I put this on my calculator, this is equal to 3.99956 if I put this in exact form. So once I've got this as my value, what we can see, this is very close. This is approximately going to be equal to 4. So essentially just round to the nearest whole number. It should be very close to a whole number whenever I do this as well. 4 is could be thought of as 4 divided by 1. So that means that right now my ratio, my end part's going to be 1, my middle part's going to be 4. Now I'm going to again divide my smallest number by my largest term. That is going to be 1.075 times 10 to the 19 divided by 1.344 times 10 to the 18. Well, I can cancel this out almost all the way. So it's just this times 10. That's going to give 10.75 divided by 1.344 approximately. Again, if I put this in exact mode, so not putting these exact numbers in, but putting in the numbers my calculator gave me exactly with all my decimals, that gives me 7.99996, which again, very close to being approximately 8, which means this value here is going to be 8. Or I can think of this like 8 over 1. So again, this value here is kind of 1 in my ratio. Then I can find 4 by doing my division, find 8 by doing my division, which means the long-term ratio of the sizes of my three age groups is going to be 8 to 4 to 1, where this population size is 8 times the size of where I end up. And this size in the middle is half of my original population size as well. It's kind of one way to interpret these results. Once I have these ratios here, that is the answer to part B. So put this in a little box. And now let's do part C. Okay, for part C, I have 2,600 people, 2,600 people. I'm going to divide each of those by my ratio of 8 to 4 to 1. This might be a skill you haven't done since like year 8, might be the last time you've done this. So to divide a value in a given ratio, I just add all my parts together. That's going to equal 13 different parts. So 8 plus 4 plus 1 gives me 13 parts. Now I'm going to write these as a fraction. That's going to be 8 over 13. And I multiply that by my original number. I can do 4 over 13 times my original number. And I can do 1 over 13 times my original number. If I do that, I get a population matrix that looks like 1600, 800, and 200. Once I've divided these numbers in a given ratio, I now want to observe what happens to my population if I multiply it by my Leslie matrix. So if I do P, I guess of K in this case, is equal to L multiplied by PO. If I use my calculator, this is going to give, if I use my calculator, this will give me 1920, 960, and 240. So this is my new population size. If I now do my division like I did before, if I divide 240 by 200, and I keep doing that across, I'm going to get approximately 1.2 again. So 240 divided by 200, it's going to be 960 divided by 800. It's going to be 1920 divided by 1600 will all equal 1.2. So therefore, if I want to times by my factor so it's constant from the beginning, my final answer here will equal 1.2 multiplied by PO. Or I could say my Leslie matrix times PO is equal to simply 1.2 times PO, where 1.2 is the growth rate of my population. So instead of multiplying by a whole big matrix, I can just scale my population by 1.2 instead for L.